In this video lecture, I will discuss the first instance where we encounter post-selection inference through the use of so-called Hodges estimator. So we're going to focus on a very simple setting to illustrate the problem. We're going to assume that we have data from a normal distribution, IID, a variance we're just going to set equal to 1 for simplicity, and we're going to focus on estimating the mean mu. Of course, we know in this case, we would typically estimate the mean using the maximum likelihood estimator, the sample mean. And we know that the sample mean has a normal distribution, it can mean mu, and the variance 1 over n. Now, we're going to consider an alternative estimator rather than just a sample mean, and that estimator is going to be a model selection kind of estimator where we say we're only going to use the sample mean if it's large enough. So if an absolute value of the sample mean is larger than the number c. If not, we're going to set the estimator equal to 0. So in terms of model selection, what we're doing is we're fitting a model with an intercept only, and if we decide that actually this intercept is not needed, which we use the rule the absolute value of the sample mean smaller or equal than c, then we leave it out of the model. And of course, in that case, a model is just of the mean would just be 0. So this is actually what we call the hard thresholding estimator. So to contrast this to what we had for the lasso, the soft thresholding, here we have hard thresholding. The thresholding step is the same. The only thing is we're not shrinking towards 0, and that makes it hard thresholding. So you don't shrink, you only put things to 0. Now let's analyze this estimator. And let's first look at the probability of making the correct selection decision. So this relates back to what we did for the lasso, where we looked at the model selection properties. Well, using again the convention that capital phi denotes the CDF of the standard normal, we can write the CDF of the sample mean, of course, as the function phi, but then we need to make sure, of course, that we properly standardize. So we standardize y bar as square root n y bar minus mu. So the probability that y bar is small or equal to x can be represented as phi of square root n x minus mu. And then we can analyze the probability that we actually set our estimator equal to 0, which of course happens if y bar in absolute value is small or equal to c. Well, we can plug in then, because we have derived the distribution here above. So we just plug it into this probability here, and we get this difference of these two entries from the standard normal CDF. Now this is entirely analogous to what we did for the lasso. Well, then we can analyze, again, entirely analogously to what we did for the lasso, we can analyze the probability of correct and incorrect selection. So for correct selection of mu 0, we want that we set the estimator equal to 0 with probability conversion to 1. Well, what is this probability going to be? It's just, well, we go back one slide, we plug in mu is 0 here. And for mu not equal to 0, we want the opposite probability of setting it not equal to 0, which is just 1 minus the probability here on the bottom half. And then, of course, we can analyze pretty straightforwardly. If we make c larger, we'll do better at putting things to 0. So we'll do better if mu is actually equal to 0, but we'll do worse of not setting mu equal to 0 when we shouldn't. And obviously there's a trade-off, and no fixed c will make you do both things. Now this was apparently not a problem when we had consistent selection properties for the lasso, and indeed it's also not a problem here if we let c depend on n. So that is what Hodges suggested. Why don't we do this estimator but with c a function of n? In particular, what he said, well, why don't we take it n to the power minus 1 over 4? Well, if you do that and you just plug everything in, then you get the probability that you set the estimator equal to 0 if mu is really 0 is phi of n to the power 1 over 4 minus phi of minus n to the power 1 over 4. The first one goes to infinity, the second one goes to minus infinity, so we get 1 minus 0 is 1. Well, that will indeed guarantee us that we set the estimator equal to 0 if we really should. But on the same hand, of course, for mu not equal to 0, we have that the probability of setting it not equal to 0 also is going to converge to 1 if the true mean is indeed different from 0. Take any fixed value for the true mean here, and then because we have a square root n in front here and only n to the power 1 over 4 here, this will increase faster than this first part, and therefore this part will dominate. So because there's a minus in front, if mu is positive, this will go to minus infinity. If mu is negative, then this will go to infinity. We do the same thing for the last term. If mu is positive, well, you have two minuses, it will go to minus infinity. If mu is negative, you have minus something and plus something, but then again the square root n here is going to win from the n to the power 1 over 4. So it goes to plus infinity. Well, if you collect that, either way you get 1. So that gives you actually consistent selection using Hodges estimator. Well, this is graphically what it looks like. So what we have here in blue is an indication of the distribution. Of course, it's not the limits of the distribution because y bar has a normal distribution, so which of course has unbounded support. But I've subtracted here 3 times the standard deviation and added 3 times the standard deviation. So it covers most of the probability, over 99%. On the green part, we have the bounds. So between these bounds, y bar is smaller or equal to c in absolute value, and we would set the estimator to 0. Well, the true mean is 0 here, mu is 0, and we see that for small n, there is of course some probability that you end up outside of these bounds. So for small n, it's definitely possible that you actually end up with an estimator not equal to 0. But when you see when n increases, the mass of the distribution tends to be located fully in between these bounds, because they decrease slower than at rate n to the power 1 over 4, whereas the distribution becomes tighter at rate square root n. So in the end, we'll end up always inside these bounds. Well, take another mu equal to 1/2 here, and you'll see that for small n, the probability of actually setting it to 0, which would be wrong here, is present and could even be quite large. But as n progresses, there becomes a clear difference between these two areas, and for large n, we will not end up inside this area where we set it equal to 0 already. Again, we need that both of these areas are going to converge towards 0. Now, so far, nothing new, but this is really what we've done for the lasso. And we can even use the same terminology of conservative and consistent selection. At conservative selection, variable screening, we look at relevant variables, where here that translates to mu not equal to 0. Well, in order to have that, we need that the Cn goes to 0, or in lasso terminology, that lambda goes to 0. Consistent selection additionally requires that we look at the irrelevant variables, so mu is equal to 0. Well, we've just done this case. What we need is that square root n times Cn converges to infinity. Or in terms of the lasso, he would say lambda times square root n converges to infinity. So far what we've done is only do the same as we did for the lasso, and there's nothing new here. There's also no contradiction or indication that we run into problems yet. But we're now going to go to that part where we run into problems. And that is, in particular, what we're going to do is we're going to derive the exact distribution of our hard thresholding estimator, which we can do because we assume normality, so that actually becomes feasible. Now this is quite a lengthy calculation, so we're going through that carefully one step at a time. First, note that if we want to derive this distribution, the probability that mu hat is small or equal to some number x star, we can split it into two cases that we have. Right? We can split it in the cases where y bar is smaller than Cn in absolute value, which is in the case where we're going to set it equal to 0, and the case where y bar is larger than Cn, where we're going to use the sample mean. Now that's exactly what we do in the next time we use that information. First of all, given that we conditioned on y bar being smaller than Cn, it means that we're going to set mu hat equal to 0 there. So we can just replace mu hat by 0. And this then becomes an unconditional probability. Now, we do the same thing over here on the right hand side, but where there we replace mu hat by y bar. Now this probability that 0 is smaller or equal than x star, well, both sides are deterministic, so it's either true or it's not true. So it's just going to be 1 if indeed 0 is smaller or equal than x star, and it's going to be 0 otherwise. So we can use an indicator function to indicate that. Now, the probability that the absolute value of y bar is smaller or equal to Cn is in fact already what we calculated when we look at the selection probability. So there we get this difference of the two standard normal CDFs. Now what I also did was actually I'm going to write back this conditional probability here again as a joint probability. Right? We have conditional 1 again times the marginal, so this would be the same as this joint probability here, which is now the terms in red. So now we get to the complicated part, and we want to show that this joint probability is equal to the sum of these two probabilities. Well, let's draw a line and let's have a look at what this probability actually means. Now, when on these lines, I'm going to put my value for C and minus C. So these are going to represent Cn in this line here. Now obviously if y bar is somewhere between these 2 points, then I will have a 0 here, because I'm not counting that probability if it's between. So it depends on where x star is, how I should count this probability. Now suppose that x star is somewhere here on the left. Well, in that case, I don't need to be bothered about this condition, y bar being larger than Cn in absolute value. And the only thing I have to count as a probability is the probability here on the left of x star. So I count the probability up to x star. Now I do this for any x star until I reach minus Cn, because the moment I go beyond Cn, I don't count that part. So I only count up to minus Cn. Now that is exactly what I have here in this first part. I count the probability of y bar being below the minimum of x star and minus Cn. Now for everything that we have in between here, I do not count anything for this probability. I only start counting again when x star goes beyond Cn. So now suppose that x star is somewhere here, beyond Cn. Well, in that case, what I should add is this probability here, of this area, of y bar ending up in that area. So that is the probability that y bar is between a lower bound of Cn and an upper bound of x star. But I also realized that if actually I was here in between with x star, then I should not count anything. So I should only start counting when x star is above Cn. And that is why we have this maximum over here. Now note that if x star is below Cn, then I have the probability of y bar being between Cn and Cn, which of course is just equal to 0. So in that way, I can rewrite this joint probability here as the sum of these two probabilities. And the reason why I do this is because now I can rewrite this easily in terms of the standard normal distribution, because now I can just use, I have y being small equal than something, so I can just subtract the mean and multiply by square root n. So that's exactly what I do here. And of course this does not change the minimum, so I can put these things inside the minimum. Same for the maximum, I multiply by square root n, subtract the mean, and put it inside the maximum. So now I've rewritten everything in terms of the standard normal distribution. And that also means that actually this whole thing is the distribution of my hard thresholding estimator. Now let's do a few more steps, because we typically want to have a distribution in terms of a standardized quantity, right? Subtracting the mean, multiplying by square root n. Well, that's now something we can easily do. Just rewrite. And then on the previous slide, you would plug in for x star, you would plug in mu plus x divided by square root n. Well, if I do that, I rewrite, I get this as my distribution of the hard thresholding estimator. So that's all well and good, and now we can start analyzing this distribution. I mean, the first thing we realize is that this is not the same as being standard normal. Well, okay, this is the exact distribution, so it doesn't have to be standard normal. We only want in the limit for it to be standard normal. So let's have a look at what happens in the limit. Well, we already had these conditions that Cn should go to 0 and Cn times square root n should go to infinity, because those guaranteed us that we had consistent selection. Well, if we use these same criteria, then we can start analyzing all these terms in here. First of all, the indicator function that says x should be bigger or equal than minus square root n over mu. Well, if mu is larger than 0, then obviously this right part goes to minus infinity. X being larger than minus infinity, that is of course true. So this will just converge to 1. We also know that this quantity will converge to minus infinity, because again, the mu is going to dominate the Cn. But on the other hand, the quantity here, where we have two minus signs, will go to minus infinity. Well, and those we can then plug into all these terms. So we get, for the first term, this converges to 1, which we have here. We have phi of minus infinity, phi of minus infinity, which we have here, which of course will become 0. We have phi of minus infinity, well actually of the minimum of x and minus infinity. So that will be minus infinity. And then we have phi of the maximum of x and minus infinity, which will be x. That's a phi x here. And again, finally, we have phi of minus infinity. Well, now you can just count them. We have 0, 0, 0, and 0. So we're only left with 5x. So, indeed, we have what we wanted. If we let n go to infinity, the asymptotic distribution properly scaled and standardized of our estimator, our hard thresholding estimator, is equal to standard normal. So that seems like it's the oracle property. Now let's wrap up the other parts, because we haven't looked at those yet. We can do mu smaller than infinity. Again, the same reasoning, but now all the terms are the opposite way. So now our indicator function will converge to 0 because x will not be bigger than infinity. This term converges to infinity. This term converges also to infinity. Again, you can plug everything in and you'll end up again, unsurprisingly, with 5x. Finally, for mu equal to 0, that's the one case that is different. Of course, we actually already know the outcome there, because we know that we set our estimator equal to 0 with probability converting to 1. Now, let's see if we can also find that in the distribution. Now, we have this indicator function, which is either 1 or 0, depending on whether x is larger than 0 or not. We now get infinity minus phi minus infinity, but we get also here plus infinity, minus phi infinity. So here we end up with 1, right? This is going to be 1 minus 0. So we're left with this indicator function. And then here we have 1 minus 1, which is 0, and this one is also 0. So we're only left with this indicator function. So what is the distribution? It jumps up from 0 to 1, which simply means that it's a discrete distribution with actually only one point, and that point is, of course, where we set our estimator equal to 0. So we have exactly found the oracle property. If the true mean is not 0, then our hard thresholding estimator has a standard normal limit distribution. And note, of course, the standard normal limit distribution is exactly what the MLE has, the one which doesn't do model selection. We also have that if mu is equal to 0, we set it equal to 0 with probability conversion to 1. So that's completely entirely analogously to what we found for the lasso. But we also saw that actually this exact distribution was definitely not normal. And that raises the question, well, what does it look like first? And then we'll look at that in the next slides. And as we will see, it really looks very, very much off. And so we have here the case that we actually hope to get, because that replicates sort of the problem that we encountered. We have the oracle property, so everything seems all good, but actually in practice it's not good. So the exact distribution here, which we can derive analytically, shows that things are not good. So it raises the question whether convergence is uniform over mu, and this we're going to analyze by trying to find a sequence, as we did for the definition of uniform convergence. We're trying to find a sequence, and now the sequence is the parameter for which the distribution actually does not converge to the distribution we want to have the limit, the standard normal. But let's first have a look at the graph. So here we see the CDF, and so the red one, the dashed one, is the standard normal, and we see indeed actually it matches the standard normal except for this area around here. So this is exactly, of course, the area where we set our estimator equal to 0, and this creates a weird jump here. So you don't end up here. CDF is flat, then you jump, so you have a positive point mass at that point, and then it's flat again. So you never end up there, which is really the area around the threshold. If you look at the PDF, it looks even nicer, because here you see it much better. We sort of follow the red shape, the standard normal, except we take a bite out of it. We take a bite out of it here, and we put all of that bite, we put on this one point only. Well, this is definitely something that looks very normal, and to approximate that with a normal distribution might be really a bridge too far. So let's have a look at uniform convergence. So what we're going to do, we're going to take a sequence mu n which goes to 0. The idea of that is that we're going to make it harder for the model selection algorithm to find the mu. So if we get more data, it becomes easier, right? You can more easily detect a non-zero mean. So we're going to counter that. We're going to counter that by making the mean smaller, letting it go to 0. So we can create a sort of persistent uncertainty. And by doing so, what we can do is replicate or approximate what is happening in small samples. If you remember the graph I showed earlier, there we could see that for the hard thresholding estimator for small n, you actually did have quite a serious probability of ending up in the wrong part of the distribution. So ending up in the case where if mu is not equal to 0, you still set your estimator equal to 0. Now this is the kind of situation we want to replicate and to approximate asymptotically. And for that purpose, we take a sequence mu n, which is going to converge to 0. Now, what we're going to do is first focus on the probability that we indeed set our estimator equal to 0. That is what we're going to first have a look at. Well, this is what we already, of course, looked at. When do we set the estimator equal to 0? Well, whenever y bar is an absolute value smaller or equal than Cn. So let's rewrite that statement here and write it in terms, again, of the standard normal. Now, this is the same expressions we had before. The only thing different is that now, instead of writing mu, I write mu n to indicate that for every n, I might take a different mu. Now, how am I going to take it? Well, let me take it as gamma times Cn. So I'm going to take the same Cn as here, and I'm going to take gamma times that one, where gamma, of course, should be not equal to 0. Well, what I can then do is plug that into that expression that we have inside here. And then I actually can take Cn out, so I get square root n times Cn times 1 minus gamma. Well, this I can then plug in, so my probability setting the estimator equal to 0 is just this expression here in terms of gammas. Now we also know that we already chose Cn such that square root n times Cn goes to infinity. That's what we needed to have consistent selection. But that means that also here we have square root n times Cn going to infinity. And that means that depending on the sign of 1 minus gamma or 1 plus gamma, we'll jump towards either minus infinity or plus infinity. So if you take gamma larger than 1, then this becomes negative, so this whole thing will go to minus infinity. On the other hand, here everything will go to plus infinity. So if we do that, then the probability that we set our estimator equal to 0 is going to converge to phi minus infinity minus phi minus infinity is 0. Same if you take gamma smaller than minus 1. Well, so far so good, because well, we actually have a non-zero mean, and it means we end up with a probability of setting it equal to 0 of 0. So that's good. Now the tricky part comes if we take gamma smaller than 1. Because now 1 minus gamma will be positive. So multiplying it by something that goes to infinity will make this whole thing go to infinity. But the other term also goes to infinity. And if you now go back one slide and notice that we have a minus actually here compared with this term, so you get minus square root n Cn 1 plus gamma, then we'll see that the second term goes to minus infinity, where the first one goes to plus infinity, and therefore we don't set the estimator equal to 0 with probability 0, but with probability going to 1. So we actually get the complete opposite result. So if we take a sequence where this mu n is just small enough, we will never find it. At least asymptotically, we will never find it. We will treat it as if the mean was equal to 0. So we do an incorrect decision, and we incorrectly set our estimator equal to 0. Of course, the one case I did not look at is when gamma is equal to 1 in absolute value. Well, there you get sort of an in-between result. That one is rather complicated mathematically, so we're not going to look into the details of that. You can have a look at the paper by Bertrand Lay, where they derive these results. Now, what is the key is the limit that we get depends on which sequence we're taking. Whereas for uniform convergence, the condition was that no matter what the sequence was, you always end up converging to the same limit. So clearly we found a case where uniform convergence does not hold. And what we did was only focus here on this probability. Now, of course, you can extend that to the whole distribution. The arguments are the same, it's just that the math becomes more complicated. But obviously, for the whole distribution, uniform convergence also does not hold. Now, the big question is, of course, how do we interpret these results? Because, well, okay, we found now that uniform convergence does not hold, but what is the meaning of this? Because we've taken a parameter which is a function of n. And how do we interpret that? Because it's not a natural way to think about parameters. when they change with the sample size. If you think about the data generating process for your economic model, then you don't think that the effect of your variables, so your beta coefficients, would change if you gather more observations, if your sample size becomes larger. So this is a very unnatural way to think about parameters. To think about parameters being functions of sample sizes. And so the way I would interpret this is by basically turning the argument around. So rather than looking at what does this mean asymptotically, we look at what does asymptotics mean for a finite sample approximation. So what we're interested in is deriving results for fixed n. Well, that's what we have in practice, right? We have one n, so we would want to have results for fixed n. Now we are generally incapable of deriving those results. So the only thing we can do is resort to asymptotics, but this is meant to be an approximation of what happens for fixed n. So if you think about it that way, and then think about the fact that, in practice you only have one n. Well, if you only have one n, then you also just have one value of mu, right? It's just a value for the parameter. So there is nothing going to infinity, going to 0 and changing mu. So from that perspective, I would argue, well, this is actually not a problem, right? If you think of it as you have one DGP, you have one sample size n, and you have one parameter mu. And now what you want to have for that one parameter mu, given your sample size, is that it should be a difficult one. One that is close to 0 but not equal to 0, one that is hard to detect. But which value we should take for that mu depends on the size of your sample. So if you have 50 observations, then larger values of mu are already hard to detect. If you have 500 observations, that same value of mu that you use for n is 50 would be easy to detect. But there is another value, a smaller one, that still is hard to detect. So what we're going to do with these parameters here, which are a function of sample size, is essentially what we're saying: fix n, and then collect a parameter that is hard to detect. Now, next step, you change n, and for that new n, you're again going to find a parameter that is hard to detect. And we string all these parameters together for different values of n, and that will bring us our sequence mu of n. And then it turns out that in order to do so, that sequence should converge to 0 with a certain speed in n. And this is exactly what we're doing by this type of asymptotics. So we're going to reflect the uncertainty that we have in a small sample of being able to detect that value of mu. We're going to make sure that lasts if I make n larger. So I'm going to counterbalance, and I mentioned before, counterbalance the effect of increasing n by decreasing mu, making it smaller to 0. So we're going to find that mu that makes it hard to detect for that specific sample size n. And by that way, we're going to make our life harder in asymptotics. Otherwise, our life becomes too easy, and it's a poor approximation of what would happen with fixed n. Now, how does this relate to what we've done so far in the course? Why did we not encounter these problems? Well, the main reason was we assumed beta-min conditions. Beta-min conditions say non-zero coefficients, in our case mu, the mean, should be large enough. Well, that large enough exactly is meant to rule out these cases, where it decreases to 0 with a fast enough speed to cause problems for your model selection criteria. So by assumption, we ruled out these cases. But of course, in practice, there's no way you can rule those cases out, because how would you know that all coefficients are actually large enough? And therefore, we need to find a way to deal with them. Now, what I will do next is I will extend this to the lasso. So use the same framework, but then see okay, if we do lasso or we do more general regression with model selection, where do the problems then actually show up?